Welcome to another video in our introductory series leading towards the Mathematics 1 course. Today I'm going to talk about a topic that some of you might actually not be familiar with, and that is mathematical induction. Mathematical induction is a proof technique in mathematics we'll encounter in some circumstances here. So I'd like to talk about the most important parts and give you an example on mathematical induction before we actually go deeper into the topics. So this is still part of the introduction. And this section is called mathematical induction. The idea of induction is pretty simple. We have a statement, a formula, for example, that we want to prove holds for every natural number. So it's a formula depending on some natural number. And the idea to do this is a two-step process. We start by showing an easy case, and that is the statement is true for some given number, for example, the number 1. We just substitute that number into the statement. We can just calculate the result, see if the statement is actually true. That's usually the easy part. The not so easy step is step number 2. In that step, we do the following. We assume the statement is true for some natural number. And using that assumption, we show that this implies the statement is also true for the next natural number. So the idea is assume the statement is true for some number n, and using this fact, show that it must then also be true for n plus 1. These two steps together then give us a proof that theorem is true for all natural numbers. And this is called the inductive principle. So the idea is kind of like a game of dominoes, right? So if you have dominoes standing next to each other, and you want to show that all of these dominoes need to fall once you tackle the first one, then it's a two-step process. Of course, you have to actually push that first domino so that it falls over. That's step number 1. And then you have to make sure that 2 consecutive dominoes are close enough. Like if there's some like this, then if that domino here falls, the next one will do nothing. If they're close enough together, then one falling domino will necessarily tackle the next one, and that will push the next one, and so on. And step number 2 is something like proving that given that one domino falls, the next in the line is also going to fall because it's close enough. That's basically the idea behind mathematical. So let's take a note of all that. As I said, the idea of this thing is we want to prove a statement that depends on some natural number. Prove a statement holds for all natural numbers. For example, that statement could be a formula depending on some natural number. We'll usually call this n. We do this in 2 steps. The first step is show the statement is true for n equals 1. And just as a side remark, that does not necessarily have to be n equals 1 really. It can be any real number. 1 or 0 is usually the most easy case to see. But the idea is that you prove the statement holds for every number large or equal to this first one. And that's why we usually start with 1 or 0. And part 2. Now what we do is we assume the statement is true for some n. Assuming the statement is true for some n in n, show that it must then also hold for n plus 1. So the idea is something like this. You have your n's, right? You start with 1, and that is proven directly. So through this step number 1, you show that this statement is true for n equals 1. Now using step number 2, you know that if the statement is true for n equals 1, then it must also be true for n plus 1, which would then be 2. So using step number 2, we can then extend the statement to the number 2. And then we just continue this process. Once we know that the statement is true for the number 2, we can again use step number 2, which will then show us that the statement is also true for number 3. And we continue doing this. From 3 we get to 4, and so on, and so on. Until finally we get to any number in the chain of natural numbers that we want. So the statement is then true for every possible natural number. And again, think of that as something like falling dominoes. Okay, so formally, here's the theorem. And that theorem is called the inductive principle. And that sums up what we've just discussed. So again, we need a statement for each natural number n. So for each n, let S of n be a statement depending on n. And then this statement is true for all natural numbers if we can prove these two steps. So S of n is true for all n in n if the following hold. One, S of 1 is true. So as I said, you need to prove the statement holds for the number 1. This is also known as the base case. Showing that the statement holds for 1, we will usually say we are proving the base case. And then there is number 2. That's called the inductive step. For all n in n, we need to show that if S of n is true, then S of n plus 1 must necessarily also be true. So that's what we need to show. And this is called the inductive step. Okay, so that's basically how this technique works. We're going to see an example in the next video. So if you didn't quite get these steps yet, please watch the example. I think it becomes a lot clearer once you see that.